In this video, we're going to talk about finding the area of regular polygons. This is something you probably have not done before, so we wanted to make sure that I put this in a completely separate video. First, let's talk about the definition of a regular polygon. So, a polygon that is considered regular is both equilateral, meaning all sides are congruent, and it's also equiangular, meaning all interior angles are congruent. The regular polygon that we've already discussed in this class is an equilateral triangle, where all three sides are congruent, all of your interior angles are 60 degrees. So when we talk about other regular polygons, we're talking about anything that is bigger. We've also talked about a square. That's a regular polygon. Then there's the regular pentagon. This is an example of a pentagon, five-sided figure. All five sides are congruent. All of these angles are congruent. The formula that we're going to use is all for regular figures or regular polygons. It's not going to be a formula you could use if you had an irregular polygon, or one where all sides were not congruent. So, what we have here is getting to know some of the vocabulary for regular polygons. I'll actually start with the center. The center is the point that is equidistant, so the same distance to all vertices. Okay, what are your vertices? Your vertices are where your sides meet. So these are all of your vertices. That makes this point here the center, because this and this and this and this and this, all of those segments are congruent. Same idea here with my hexagon, six-sided figure, to the vertices. Those are all congruent. We would also then call all of those segments from the center to the vertex a radius. So that's considered the radius of your regular polygon. It's a big distinction between that and the segment that we are calling the apothem. The apothem is going to be labeled with a lowercase a. That's why we were talking about on the previous video, we need to have lowercase, or distinction between lowercase and capital. The apothem will also start at the center, but it goes perpendicular to a side. What it also does is it bisects that side. So it is, because it's a regular polygon, that segment is the apothem. It is perpendicular to your side, which is going to become really important, and it bisects that side, which is also really important. The last big vocab word here that I want to talk about is called the central angle. Central angle is formed by two consecutive radii. So in that case, that's all of these red dashed lines here are radii. They form a central angle. This here, that angle that's formed between those radii, is a central angle. There's 1, 2, 3, 4, 5 of them in a pentagon. There's 1, 2, 3, 4, 5, 6 of them in a hexagon. Because they would all form what is sort of like a circle, all of them add up to 360 degrees. The other thing that's important to know about them is that in a regular polygon, all central angles are congruent, which helps, because that way I know that in a hexagon, there's 360 degrees all the way around, and there are 6 congruent angles. I have 360 degrees being divided by 6 congruent central angles. That makes each central angle 60 degrees. That's a 60 degree angle, 60 degree angle, 60 degree angle, and so forth. With a pentagon, all the way around is 360, but there are 5 central angles. So using my calculator with the pentagon, 360 divided by 5, I know that each of these are 72 degree angles. All 5 of those are 72 degree angles. Now what that doesn't include is this angle formed from a radius to the apothem. That's not 72, that's not a central angle, only from the radius to the radius. But, and this is tricky to remember at least, this apothem bisects your central angle. So if that's 72, then you have a 36 degree angle and a 36 degree angle. If that's 60, this apothem cuts it into a 30 and 30. Really key idea that we're going to talk about shortly. Why? Well, here's what we need to know for area of a regular polygon. Capital A is your area. It's equal to 1/2 of the apothem times the perimeter. Capital P is the perimeter. Think of an apothem as the height of your triangle. In all of these instances, we're assuming that the shapes that we're looking at are regular polygons. We're not going to look at any polygons that are not. Therefore, since I know that this has a perimeter of 24 and it's a regular polygon, it has 1, 2, 3, 4, 5, 6 congruent parts. In my formula, I'm going to plug in 1/2 the apothem, I don't know, times the perimeter, I do know, is 24. In order to find the apothem, realize that if this is my center, that segment which is perpendicular is my apothem. Here's how I'm going to have to find that length. I know that all the way around is 24, and that there's 1, 2, 3, 4, 5, 6 sides. Since it's a regular polygon, all 6 are equal. That makes all 6 sides 4 millimeters. 24 divided by 6. I now also know that this side is bisected, so I have 2 and 2. Draw in a radius. And what we have here is a right triangle. Draw in your other radius down here, and you've formed this big angle as a central angle. So we are really going to be applying some key pieces of information here. That big angle in a hexagon, there are 6 big angles. That big angle, that central angle, is 60 degrees. And since my apothem bisects it, I have a 30 degree angle here and a 30 degree angle here. What I'm really focused on there is this idea, this part of that triangle. That's my apothem. That's 30 degrees. That's a side length of 2. So what I've done there is just take this triangle here and I pulled it out and I'm looking at it separately. Because now I can apply my 30, 60, 90 relationships. We know that opposite my 30, I will call just side length x. Opposite your 60 is x square root 3. We should know that from our trig unit. Which means that if my side length here is 2, my apothem is that x, 2, times the square root of 3. That's what I plug in for my apothem. So I had to use my 30, 60, 90 relationships. Okay. If I wanted an exact answer, I'd have 1/2 times 2 is 1 times 24. I'd get 24 square roots of 3 millimeters squared. But it does say round to the nearest hundredth. That gives me an area here of 41.57 millimeters squared as my final answer. This second example, example 2, we're going to do in a similar way, but it's going to work out a little different. You still need to find that central angle, but this is a 1, 2, 3, 4, 5-sided figure. That makes it a pentagon. That makes this central angle here 360 divided by 5, or 72 degrees. So your apothem that you have to draw in, perpendicular, cutting this side in half, makes angles of not 72, but half of that, 36 degrees. So I'm going to pull this triangle out. It is no longer a special right triangle. This is 36 degrees. There's my apothem. This side length is here. Well, since it's regular, and I had a side length of 16, that divides in half as 8 and 8. Okay. We know our perimeter is 16 times 5, 1, 2, 3, 4, 5 sides, which gives me a perimeter of 80 meters. The apothem is what we don't know. So I'm going to use something else we've learned recently. It's not a special right triangle, but it is a right triangle, and I can use my trig functions. If this is my reference angle, 36 degrees, I know my opposite, and I'm trying to find my adjacent. Opposite and adjacent is my tangent function. Tangent of my angle, 36 degrees, is equal to the opposite side, 8, divided by the adjacent side, which in this case is my apothem. Okay. When I solve this, I get the apothem is equal to 8 divided by my tangent, and rounding it to the nearest hundredth, my apothem is approximately 11.01 meters. I now know the two pieces of information I need to calculate my area of this pentagon. Plug everything in, put my calculator in the correct mode, 440.4 meters squared. In class, we will talk about more examples, and especially we'll look at these examples 3 and 4. Go ahead and rewatch that video if you are struggling. We will also look at number 5 in class. Very quickly, I'm going to talk about this area of circles. What you have to recall is our formula, pi r squared, where r is your radius. So if I give you a radius of 4, your area is pi times 4 squared. Now the difference between exact and estimated. Exact answers have pi. Estimated answers, we use 3.14 and multiply. Okay. So 4 squared is 16. I have 16 pi square feet. That's an exact answer. But that's not a realistic answer if this were an application problem. If I had asked you to go out and measure something, or measure a circle, find some area of a circle, you're not going to come back and tell me it's 16 pi. I'm not going to be able to do anything with that. If I need to buy materials, I can't go and say I want 16 pi square feet of that. I have to give them a specific number. That's why we take it and multiply it by pi, or 3.14 as an estimate for pi. 16 pi is the same as approximately 50.24 square feet. That's estimated. Exact will have pi. And we'll talk real quick about number 7 in class as well.